So let's start with the introduction of the subject. So this morning we have seen two kind of development of the theory of free probability by Ron Speicher with rational functions and by James Mingo with the transpose. And so now we are looking at another direction, and which is more focused on a different distributional symmetries than what we are used to do usually. So, as you know, compared to classical probability, we have a kind of sophistication, which is non-commutative probability. So there is a classical notion of independence. Which is actually called tensor independence, and there the notion of free independence. Right? And what I'm presenting now is a second sophistication that I called traffic probability. Which comes together with a notion of independence that I call traffic independence. And which has the property that it encodes both the notion of free independence and the notion of tensor independence. Moreover, let me note that there is also a third notion of Boolean independence, which in a different way is also encoded by this notion. So somehow this will unify the two point of view there. Moreover, we know that typically a good model for free independence are large unitarily invariant matrices and this is a point I want to focus in the title. There, the good model for that is something which is more general, is large permutation invariant matrices, which means invariance by conjugation by permutation matrices. So this is the general picture, and let's see what is the motivation to introduce this program. So I introduce a matrix model, which is the adjacency matrix of what is called the Erdős-Schwenny graph. So it's a complicated name for a very simple model. You consider Xn, which is a real and self-adjoint matrix whose entries are denoted Xaj. Such that subdiagonal entries are IID, and the entries are either 0 or 1, and the probability that Xaj is 1, we assume that this number is of the form d over n, where d is a positive constant, which is fixed. Okay, so it's a very, very simple matrix. So Ryan, who was a student of Ron Speicher, proved that independent copies of Xn are not asymptotically free. a p-tuple of such matrices will converge in star distribution. Ryan proved some formulas for the cumulants of these variables, but they are not asymptotically free. And what I realized during my thesis is that if we consider AN, say this is a deterministic matrix, then the possible limiting distribution of the couple Xn AN depend on more than the limiting distribution of AN. So if Xn is a Wigner matrix, which means that there you divide by square root of n, and then you put any distribution there which does not depend on n. You know that independent copies converge to free semicircular variables, and that given a deterministic matrix that converge in star distribution, the limit of this object is just a free product of the distribution. And there, with that model, you can compute exactly what are the ingredients on AN you need to understand the joint distribution. And these ingredients, you call it some traffic distribution. You give a name to this data, and actually, you can create that theory, which is similar to free probability, but given with a different notion of distribution. So what I'm going to introduce today is what is this notion of distribution and how this give us a kind of asymptotic freeness theorem. Alors, tableau monté. Bon. Okay. So first, I'm recalling the theorem of asymptotic freeness for independent random matrices. So the first version of this theorem is, of course, due to Voiculescu, and the version I'm stating now is due to Collins and Snady. I consider AN1, ANL, which are independent families of matrices. So each symbol, so this is a bold symbol like this, it denotes a family. So the matrices of each family may not be independent, but the family A1 is independent from the other families. We assume three assumptions. The first one is the distributional symmetry. We assume that for each L, the family is unitarily invariant, which means that if I conjugate all the matrices by a unitary matrix, I'm not modifying the law of the tuple of random matrices. The second assumption is an assumption about the convergence of the matrices. We assume that A and L converge in non-commutative distribution, in star distribution. And, let me recall this notion, which means that for any star polynomial, in the variables that are in the matrices, the expectation of 1 over n the trace of P of A and L converges to the trace phi of a polynomial in AL for some non-commutative random variables AL. Right? And we assume furthermore a concentration property there. For instance, the convergence of 1 over n the trace of the polynomial in Ln holds almost surely. Then, the families of matrices are asymptotically free. That is the expectation of 1 over n the trace of any polynomial in all the families converge to the linear form phi of P in A1 AL, where the distribution of each family is like it is given there, and the families A1, A2, AL are free. Okay? And so, what we can do with traffics, what we want to do at the beginning, is to have this kind of theorem where here we replace the unitary invariance by permutation invariance. So the symmetry of the model is much weaker. And the result of that is that the convergence assumption must be stronger. And we will assume not only the convergence in star distribution, but something stronger that I call convergence in traffic distribution. I will give a heuristic for the name traffic, just take it as a word to describe this. And the formal distribution of that will be very similar. We will assume the convergence of the expected normalized trace, not only of polynomials in the matrices, but on more general functions that we called graph polynomials. And I will give the definition of graph polynomials. So, for all G graph polynomial, we will assume that the trace of G of AN converges to the trace of G of A in some abstract space that we call a traffic space. So we define some new algebraic structure for that. There will be also a kind of concentration assumption that can be formalized in terms of a factorization property. I'm not going to describe it, but it is quite easy to handle, but I want to focus on these two main assumptions. The result of that won't be that the matrices are asymptotically free. In general, they are not. But we will get a relation between these matrices that we will call asymptotic traffic independence, which implies that 1 over n the trace of G of the matrices in expectation converge to some phi of G of A for any G which is a graph operation. And then they are not free, but traffic independent. So this is a picture. This is not exactly a very well-defined theorem, as most of the terms are not defined yet. What I'm going to define is the notion of traffic distribution of matrices. I will give the idea of the algebraic construction, which allows to consider this kind of object. I will not give the definition of traffic independence, because as we will see, it will involve a lot of combinatorics, so big formulas that I don't want to describe today. Right? So this is a program. But before going further, let me just give a remark. Is that if a family of matrices is unitarily invariant, of course, it implies that A and L is permutation invariant. Because the group of permutation matrices is included in the group of unitary matrices. And as a result, if you fulfill the assumption of Voiculescu theorem and moreover converge in traffic distribution, you can also apply this theorem of traffic independence, which implies that traffic independent encodes in some way free independence. Which means that for certain traffics, traffic independence means free independence. For some other traffics, this is not true. For instance, if I take AN, BN, which are independent diagonal matrices, so let's say they are just matrices, A and B, not families, we don't need that. And I assume that Bn is permutation invariant. Then AN and BN are tensor independent. And with respect to the expectation of the normalized trace, this is true for any n. So this is true in the limit. But you can apply this theorem for this kind of matrices. You can find matrices of that kind which fulfill these assumptions, which means that traffic independence encodes both free and tensor independence. And this is for the expectation of 1 over n the trace. Right? So we know a priori that if we are able to construct a theory to support this theorem, we should get that property. And this is true. We can do that. There is also a relation with Boolean independence. I won't talk a lot about this, but I just have to mention that this is with respect to another state, which is not the normalized trace. It is phi n of A, which is the sum 1 over n, the sum of all the entries of the matrix, not only the diagonal matrix, the diagonal entries. And let me clarify a bit what is this kind of situation. For certain matrices, or for certain kind of traffics, with respect to this linear form, traffic independence implies Boolean independence. And this is what I mean by it encodes independence. Right? OK. Alors, let me check. Tableau 2. OK. So if we're okay, I push you. If you have a question right now, we can stop. Okay? Okay. So let me describe what are traffic spaces. And it is much more clear when we specify for matrices. Because everything is very explicit and just depends on some very clear intuition. So I will compare with the classical theory. And in the classical theory of linear operators, so the basic operation between linear operators is this linear pattern. So if I have 4 matrices, I know how to do the product of matrices, which is just the linear composition of operators. I have there an input space, and there an output space. With traffics, so this is a kind of object which is not just a linear object. It is an object that we can compose following a scheme given by any graph. So I still have what represents an input and output space, but now I can compose, for instance, 2 linear operators in parallel like this. For matrices, there is a definition, an explicit definition of that. I can allow to have self-loops, to have arrows in a reverse direction, and arrows going to our dead ends like this. And so I'm going to define now the formal object that represents this operation. So I consider X, which is a set of formal variables, like indeterminate. They just mean symbols. And I'm defining what is a graph monomial G, and I will denote the set of graph monomial G of X in the variables xj. And this generalizes the set of monomials in non-commutative indeterminates. So this is the data of such a picture. So this is a finite connected graph so with vertex set V, H set E, such that we can have a single loops, self-loops. We can have multiple edges in any direction. So I assume that I have a labeling of the edges by the variables of X, of the family X, which is encoded in a map gamma from E to J. And J, this is an index set for the variable. So that age E has label X gamma E. So like this, I know that at the end I will put the matrix A1 there, the matrix A1 there, A2, and so on. Okay, this is given by G. And I'll also assume that I have 2 given vertices in and out in V, which are possibly equal. this is something that I allow, and we will see what it represents for the graph operation in a few minutes. Okay, that's it. This is, for us, the generalization of non-commutative polynomials. And the generalization should be read as that pictures. Now, let's define what gives a graph operation like this applied to matrices. So I have G, which is such an object, and I want to define what is G of AN for AN, which is a family of matrices indexed by J, the same label set as the set of variables there. And I will give a formula for the entry AJ of this matrix. And before that, let me recall something very familiar to everyone, which is the entry AJ of a product of matrices. So this is something which is just given by the definition of the product of matrices. It is a sum over the indices A2, A3, AL-1 of the complex number consisting in the first matrix, take the entry A, A2. For the second matrix, I take the entry A2, A3, and so on, until the last matrix with entry AL-1, J. And here, there is a summation and a product that will appear here. What we are doing in that situation is as there, okay, maybe it's L. Okay, we don't care. It's a summation over the vertices which are neither the input and the output. We choose an index for each internal vertex. So formally, I consider a summation over phi. Phi is not the state. Okay, let's put that phi. From the set of vertices to the set of integers from 1 to n. And as I don't want to specify a value for the input and the output that are given by these integers, I include this in this condition. Phi of the input is j. Phi of the output is a. So this corresponds to this summation. And now I do a product of complex numbers for each edge in my complicated graph. I have fixed some A P, A Q, and I have a matrix there. So I just consider the product of the complex number, which are the corresponding entries of the corresponding matrix. Formally, I do the product over the edges that I denote V, W. The edge E is associated to the matrix gamma E. And I take the entry phi of W, phi of V. That's it. We have defined what is a graph operation in matrices. Huh? Phi, you're right. And so it is a bit abstract now, but the traffic distribution of the family of matrices is the data of the expectation of 1 over n the trace of these matrices. Okay? And let's see examples of such matrices. Alors, ah yes, I cannot. Okay, let's do something else. I want to get to keep this formula. So let's give example of graph operation in matrices. So instead of putting formal variables on my graphs, I directly put the matrix. And this just means this graph operation at play 2A. And by definition, this is nothing else than A, because it coincides with the picture with monomials. And you can check it with this pattern, with this formula. You do not have internal vertex, so the entry AJ of this matrix is just the entry AJ of this matrix. So this is the same matrix. If now I consider an edge from the output to the input, this is the same formula, but I reverse the two entries of the matrices. This is a transpose. So transpose of a matrix is not a polynomial in the matrix, but it is a graph monomial in the matrix. So I told you we will look at this example of two parallel edges. And let's do the computation explicitly. So we want to compute the entry AJ of this guy. There is no internal vertices. So there is nothing to do about this summation process. And then we have this product, which is consisting in taking the matrix A, taking the entry AJ, times the same for B. So this is the entry-wise product. Which means that the entry-wise product is a graph operation in matrices. And if you assume that matrices converge in traffic distribution, the expectation of 1 over n the trace of A, or let's say a polynomial in A, Hadamard product or entry-wise product, a polynomial in another polynomial in A, so this is the entry-wise product. This will converge as n goes to infinity. And this brings a lot of information about the matrix model. For instance, if in the limit when n goes to infinity, this is very close to the product of the trace of P times the trace of Q, it tells you that your model will have very good properties with respect to free independence. So this is a corollary that it is described in my paper. So this is something which is easy to handle. You can compute exactly just the limit of this, and you will really get information about your matrix model. You don't have to understand all the distribution. Okay, let's consider this example where the input and the output are equal. So we go back to the definition. I have the entry AJ. I want to compute this. There is no internal vertex, so I don't have to choose a map phi there. Yet, I have this condition that input and output must have image J and A respectively. So if A and J are not equal, I cannot find such a map, which means that I will have 0 except if A equals J. In other words, this matrix is diagonal. And a graph operation with input and output are equal will always give you a diagonal matrix. And then, what is this matrix? We have the entry AJ, or AA, which means that this picture with input and output equal is the diagonal matrix of the diagonal element of A. And this is a graph operation. Another example, last one, I'm going to give today. So as before, Input and output are equals. So we know that we will get a diagonal matrix. But now I have an internal vertex. This vertex is neither an input nor an output. If I want to compute the entry aj, so I will get 0 if A and G are distinct. And then I have this summation process, which concerns this vertex. So I choose an index k to denote the index there, that I sum from 1 to n. And the entry is AK, which means that this matrix is the diagonal matrix whose ith element on the diagonal is the sum over the line. No, so let's say K. And this is a matrix that I call the degree matrix because for adjacency matrices of graphs, this gives us what is the degree of each vertex.
What's the difference between those two? The last two?
They are the same. No, I'm just, this is the conclusion of this computation. So here I compute the entries, and here I conclude about the matrix.
The one above it?
So here I have a self loop.
Yeah.
And here I have a single edge. So this vertex is not equal to that one. I have a simple edge on the self loop.
Why do you say n equals out if they're different vertices?
But so input and output refers to some vertices of the graph, not of the edge. And so I can, if you are given any finite graph, you decide which has input and the output, and it does not depend on the detail of the graph. It's your choice. Okay, so maybe we have 5 minutes. Okay, so I'm not going to detail a lot what is this notion of independence and how to handle distribution. What I'm going to give is some corollaries. So there is a step which is how this things works, but still you will have some idea of what we can do. Alors, this, number 3. So I take Xn, which is a unitarily invariant matrix, and it will work for a family of matrices, but let's consider just a single matrix that converge in star distribution. So, under a factorization property, which is a kind of algebraic version of concentration, I'm not describing that, Xn converges in traffic distribution. And the limiting traffic distribution of Xn has a very specific shape, which is related to non-crossing partitions, which allows us to deduce a lot of things about operation of Xn we can do. For instance, we can extend Mingo and Popper result about Xn and the transpose, and together with the degree matrix I just have defined, they are asymptotically free. First order. We do not consider the second order, which is a much more fine problem, which I think only concerns the two matrices. I won't be second order free with the degree, I'm not sure. Okay. Moreover, so if now I consider xn and yn, which are two matrices as before, if I consider the tensor product of xn and yn, this is no longer a unitarily invariant matrix because of that product. Yet, it remains true that it is free independent with the transpose. So it's asymptotically. And this is just one part of this application, because this is not only true just for unitarily invariant matrices, but it's true for any family of matrices which has the same traffic distribution as a unitarily invariant matrix. This is something, a subtle difference, but let me give you a very concrete example. Of matrices which are definitely not unitarily invariant, but yet have the same traffic distribution as unitary invariant matrices. For instance, so for a bond Wigner matrix, where either, so which is either periodic, which means that there we fill it with what we want to have something periodic, or such that, so, okay, and say on proportional growth, or the n going to infinity, but slower than n. So this matrix is definitely not unitary invariant, but if you take independent copies of such matrices, it has the same traffic distribution as unitary invariant matrices, which means that the conclusion of this theorem are still true. This example is due to Benson. And similarly, I told about the Erdős-Rini graph, and we were in the situation before where we have this shape for the probability that xj is 1. But if now you assume that this dn goes to infinity, even with a logarithm of m, which means that your matrix has a lot of zero, it remains true that such a matrix, when it is well normalized, you cannot differentiate it with a GUE matrix. It has the same traffic distribution, which means that we will have these properties, and these matrices will be asymptotically free from deterministic matrices, even if they are far from being unitarily invariant. But they are, so this one is even not permutation invariant, but still the theory still applies for that. Okay, and I think it's time to stop.